let people exchange the rooms a little bit, but so basically I will be talking about collaboration that we had between Bayer and Serbian Institute for Artificial Intelligence Research and Development, building this VerifAI project, which was basically part of NGI, so Next Generation Internet Search program by European Union. Basically, let's start with asking a question like, how reliable are large language models? So if you ask large language models, for example, like how many rocks should I eat each day, it may take article from Onion as kind of like the most relevant document and answer you according to University College Berkeley, geologists, people should eat at least one small rock a day. So like basically LLMs are not really understanding the context of the questions. They don't understand what is the context of the source, how relevant it is, and so on. Similar comes when you ask, like in Google or Gemini, like cheese is not sticking to my pizza, what should I do? It will answer you to maybe use some non-toxic glue and stick your cheese to the pizza. There is as well like a lot of problems with like tokenization. So like if you ask what is larger, 9.9 or 9.11, it will tell you that 9.11 is larger than 9.9 because 11 is larger than 9. And there is a lot of inherited biases. So like a couple of months ago, if you ask like, do Israelis deserve to be free? It will tell you, of course, they have like the right of self-determination. But if you ask the same question for Palestinians, it will say that it is very complex questions and there are like different views and so on. And there are like a couple of more of examples of this as well. Like they don't understand, for example, like historic context. So basically, LLMs on their own are not really reliable, and kind of like fine tuning doesn't really like pre-training doesn't kind of like solve this problem. So like we need to go a bit further to solve some of those problems. Like basically LLMs are hallucinating and they produce answers that appear coherent, confident, and articulate, which kind of like projects that they are knowing what they are talking about, while they are actually quite often talking quite rubbish things. Basically, the information that they convey may not be correct or verifiable. And the limit is basically internal knowledge that they have been pre-trained on. Basically, it limits their ability to kind of like deliver a factual answer, particularly within specialized field. And this is really a problem, especially in the fields like biomedicine, where like mistake can cost human lives. Like you basically can't afford unverified answers, and there is like a lot of other issues when it comes to biomedicine. It is like a very regulated industry, so a lot of care is taken about like data privacy, sovereignty, security concerns, and it is often necessary to build the systems that kind of like run on the premise and are not sending any kind of like data to external APIs, so you don't have any leakage of the data. So quite often you want answer that may end up in like patentable information. You don't want OpenAI to have the data that you're going to patent. Like what you can do. So there are like several ways that I think several people have been talking about, especially like there is like retrieval-augmented generation. So like we had as well previous talk that was using retrieval-augmented generation. You can do fine-tuning the model as well. That kind of like helps, but all those things don't really prevent it at all, like totally. So what else you can do? You can kind of provide sources, which is something that do a lot of systems, such as Perplexity, such as Elicit, such as so on. However, quite often when you go to those sources, they don't have really the information that the answer generated. So there is still potential for hallucination. You need manually to check the sources. So yeah, basically we have tried to kind of like combine all the approaches with the AI on top of it to actually check the sources. So yeah, like basically this is architecture of the system that we have created. And yeah, like how this works is basically user would ask a question in natural language. This question would be first sent to the search engine. We use two search engines, like one for lexical queries. So we use for this like OpenSearch. So in case you didn't hear about OpenSearch, it is basically fork of Elasticsearch, very similar way how it works. And as well, we use a vector database, which is Quadrant. So combination of that would allow us to basically find the hits that are exact match, but as well find the hits that don't match exactly, but have kind of like similar meaning. We have done a lot of evaluation on like how to combine those things. I will talk a bit later about that. We retrieved the top publications, in this case from PubMed. We use this like MS Marco DistilBERT base for vectorization of documents and storing storing the vectors in Quadrant. MS Marco is information retrieval data set built by Microsoft based on Bing queries and Bing retrieved documents, so it's very appropriate for search applications. We retrieved the top 10 documents. We built the prompt. Prompt contains instruction, contains user query, contains top 10 documents based on which the answer should be generated. We send that to a generative component of the system. This component is based on Mistral 7 billion parameter instruct model that have been fine-tuned using the dataset that we have built that we called and we published the dataset. So like it's called PQA-REF dataset. It's based on PubMed Q&A dataset. However, we have kind of like collected the relevant documents and generated the answers, so like you can fine-tune similar models for actual question answering. This would generate the response. The response is then like parsed to the sentences that are referenced. Then there is like the second model that actually checks whether there have been any hallucinations in the generated sentences that have been referenced. And this is basically done using, this is model that is based on the BERTA, and it's fine-tuned using SciFact, the dataset that have been published by LNAI. And then user gets the answer with like highlighting of like what sentences he may need to kind of like double check and that may have no evidence or some kind of like hallucination. yeah, like basically we have like three components. One is this like information retrieval, one is generation, and one is verification. So like let's maybe have a deep dive into each of these components. So yeah, like information retrieval system, basically the main idea is that it retrieves the relevant articles for generating the claims. It's based, so like we have index PubMed. So like PubMed, in case you don't know, is repository of all biomedical literature, like abstracts in biomedicine that have been published since 1940s onwards. And it contains about like 35 million publications, and yeah, it's pretty comprehensive source of information. It contains only abstracts, so we don't have access to actually full text documents, because like most of them are kind of like closed access, and you need to pay for that. Yeah, like we basically index title and abstract. They are concatenated. We excluded abstracts, like articles that miss abstracts. So they're like old abstracts, especially from 1940s and 50s, that would have only title, or they're like some kind of like reports that would not have really a proper abstract. The documents that have more than 512 tokens, we do some text segmentation in order to be able to like vectorize them and put them into a vector store, so in quadrant. The reason is because like the BERTA and BERT-based models quite often have like 512 token context length. And then like we have basically, as I said, two components, lexical search. So this is like based on open search, like it uses sparse vectors and BM25 algorithms, and we as well like index some of the document metadata such as author names, publication dates, and journal names. At the moment, we are not using anything apart from publication dates, so you can filter by date, but in the future we have an idea as well to allow users to filter by, for example, like journal names, or do some ranking based on impact factor and so on. So yeah, it is all based on open search. And then like semantic search, it uses like dense vectors. Embedding is done by BEncoder for asymmetric semantic search, so like fine-tuned model based on MS Marco dataset. As I said, this is the dataset that is particularly tuned for search. We use quadrant vector database. Initially, we started with like 32-bit like full precision. However, that we realized quite soon that searches took quite long, so that was like 40-50 seconds. And then like we quantized them to like 8-bit precision, which gave us like still quite good precision and quality of like retrieved documents, and brought down the search time to like half second, which was like increase of, well, almost 100 times. So yeah, like we use basically a hybrid search, so that is like a combination of lexical search and semantic search. How that works is that we basically, when we have a query, we fire them to both search engines in parallel, retrieve top documents, and then we basically normalize them based on the score of the top document. So like everything is divided by the score that is retrieved on the top documents. Therefore, for each document, you get the score between 0 and 1, and then the scores are kind of like added up. So like if the same documents have been found in both searches, the scores are added up, and therefore this document will get higher up. And then as well, like for each search, they are not kind of like added as 50-50, but we have like the weights. The weights are kind of like parameters of the model and can be adjusted. We did quite some evaluation. I will talk a bit later about this evaluation on BioAsk dataset. So that is as well dataset, I believe, published by National Institute of Health, where basically labelers manually annotated the most relevant documents based on the queries, and then like even provided the answer, kind of like expert answer based on the most relevant documents from PubMed. So for generative component, we created this PQI ref dataset. Basically, we randomly selected about 9,000 questions from PubMed Q&A dataset. And for each of those documents, we retrieved the top 10 most relevant documents and generated the answer using, well, at the time, GPT-4 Turbo. And there was a prompt saying basically answer the question using relevant abstract provided up to 300 words, reference the statements with the provided abstract ID in brackets next to the statement. So the structure of the prompt was that like it had a abstract ID and then like title and abstract, and then you had like 10 of them. Yeah, like then we basically fine-tuned Mistral 7B model using LoRA. So the data set was split on like 80% for training, 10% for validation, and 10% for testing. We use kind of like 4-bit quantization, I believe. So basically the model ended up pretty small, fitting into 16 gigabyte of RAM with everything, and it was like trained on single DGX NVIDIA A100 40 gigabyte instance in National Data Center in Kragujevac here. In Serbia, and basically the model had 27 million trainable parameter, and it took about 32 hours for 2 epochs of batch size 1. And then finally we have verification engine. Here is basically the architecture. So what we get is basically we have a query results of like 10 abstracts, we have a generated response, and then we kind of like parse all of those things and pass it to the Berta or Berta large model. So like those two were something that we experimented with, and this is basically how the prompt looked like. So like we had like the class token, we had a generated sentence that was reference with some abstract, and then this reference was kind of like there was like separation token, and then the document that this generated claim was referencing, and then like again separator. And the data set basically contained 3 classes, so there could be contradiction, so the claim contradicts the original document. There could be support, so like it's supported by the evidence, and there is no evidence in the document, so like the document that is referenced is kind of like irrelevant for what has been generated. And generally, this is quite long standing task in NLP. It's usually called textual entailment. However, it was not really kind of like used for verification until maybe a few years ago when large language models started appearing, and this task really became very relevant and yeah, like we fine-tuned the model with SciFac dataset. Again, there is like split of 80-10-10. And now we can go for results. And these are the results for our information retrieval system. On one side, you can see our kind of like response times. So basically, if we use only kind of like lexical search, it's very fast. So like it takes 200 milliseconds to get it, but even if you kind of like fire both queries at the same time, it takes less than a half second, so it is quite user-friendly, and yeah, like people basically don't notice this kind of latencies. So the bigger problem is basically the generation. On the other hand, you have the scores of mean average precision and precision at 10. So like basically how many really relevant documents have been retrieved in the basically top 10. And this is like pretty good score. It's like, it doesn't really look like, but for basically information retrieval, if you're quite happy when you get these results. So it really kind of like worked really well. And the best results we are getting for kind of like the weights of 0.7 for the lexical search and 0.3 for semantic. This is kind of usual or expected, since exact matches is something that users would expect to find first, or to be actually referenced and cited first, rather than something that talks about same topic, but it's not really having the exact match. For generative component, we have tested or compared with the GPT-4 Turbo, and then like we fine-tuned Mistral 1 and Mistral 2 versions. Basically, the first table shows of how many answers out of certain test set that we had how many references. So GPT-4 Turbo had like the most answer with only single reference. So references on only single document. However, M1 and M3 had like between 2 and 4, which is like much better because it uses a bit more references. Since PubMed Q&A dataset is created by PubMed abstracts that contain question mark in the title, we knew what is the most relevant document, the document that has this in the title, right? So we could as well check how, like in how many times this document was actually referenced, and how many times it was missed. And the scores were quite good. Like GPT-4 Turbo was still slightly better, but it's way larger model. It's like almost like 1 trillion parameter model, while with like 7 billion parameter, like or like quite some orders of magnitude smaller model, we are getting like 1% performance loss. And we did as well evaluation whether like the answer contains same conclusion and all information as the ideal answer made by human annotators, like basically it contained like 80–90% of information similar to what humans were doing. Similarly, verification engine was as well having F-score of around like 90%, which was quite good. So like in most cases, it would be able to spot hallucinations. And then we built as well like user interface. You can as well like try it, register. So it's all available at app.verify-project.com, or you can just like search for Verify Project on Google, and basically you can sign in. Then you have basically Google-like interface that looks kind of like this, with a kind of like search bar and verify. On the side, if you click, you get this panel where you can play a little bit with the parameters, so you can have like hybrid search, or you can select which search you want. You can select which weights you want to assign to each type of the search. You can select whether you want what number of top documents you want to retrieve. You have a selection of temperature. You can filter by dates. And then basically, if you ask a question, for example, what have I asked, like what genes play a role in breast cancer, you get answer that looks like this. So like the blue things are the references to the PubMed. This is unfortunately too small for you to see. And then once and the boxes are the relevant PubMed articles, you can click on both boxes and the links. And if you hover over for example, this green area, you get that like it is supported. This is the reference, so you can click on it, you get to the PubMed, and you get as well the closest sentence by vector similarity to the abstract. And yeah, like you can kind of like compare this to the Perplexity. So like we got about like 100 and something thousand in funding that we still have not totally spent. So we're still a bit working on it. And Perplexity have basically raised numbers of hundreds of millions of dollars, and it's valued between like 8 and 9 billion. However, if you kind of like go to some kind of like pharma perspective, like why don't we just license Perplexity? You have like a couple of problems which could be solved with the open source tools. So like, firstly, you don't have programmatic access. You can just like type the question, get the answer, and that's it. You have no possibility for granular control. Here you basically have in the system, I mean, it's open source. You have every control that you can get. You can modify it as much as you want. And it does not have access to internal information. So, I mean, here the application works really on the PubMed, but theoretically you can extend it to basically like any type of documents or anything that you have internally in your corporation or your organization, and just do the search. And yeah, like it is valuation is like 7 and 8 billion euros. And lately we did as well like quite some modifications, so you can have your own deployment. It's quite easy to deploy. You can go just to our repository on GitHub, download it, run a couple of scripts. These scripts would install Docker images with OpenSearch quadrant. You don't need to do much. Just point it then like to folder where you have like Word documents, PDF documents, PowerPoints, text documents, MD documents, or whatever you have, and it will index them, and then you can use basically the system on your documents. So I think it's quite handy, and as well, like we extended it that it doesn't use only now Mistral 7 billion parameter, but you can connect it to OpenAI, Azure. You can connect it to your open, like self-hosted deployment of VLLM or Olama or NVIDIA NIM. So like basically anything that supports OpenAI kind of like format of instruction or JSONs that are sent, which is now industry standard. And yeah, like basically nothing goes away from your deployment. You have all the security, all the privacy of your data. And yeah, like we can basically consult on deployment if you need some help. And for future, there are like things that we are thinking about. There's like semantic tagging, long-term hosting solutions. So like we are buying now GPU. Currently, it's hosted on a cloud. Document authoring is like one thing that like we may have like one tab where it will help you to create a new document based on the documents that you have indexed. Incorporate feedback from the users, so something similar that we have seen on the previous presentation, but as well kind of like involve the community and kind of like build the community around the project, so it kind of like grows overall, and generally kind of like foster the trust in generative AI across various domains. We have a number of publications published on both like ACL and quite kind of like good conferences, I would say. We are writing a journal paper right now that will combine them all. And like all would not be possible without team and funding. So we had me and Lorenzo working on the buyer side, and there are like quite a few people, Della, Boena, Milos, Daria, Natasha, Angela, and Petar working from the side of Institute for Artificial Intelligence, and as well like I would like to thank our funders from European Union and NGS Research Initiative, and that's basically it. So like thank you for attention, and if there are any questions, I would be happy to answer, and you can get in touch on all of those social media and websites.